Hey everyone, welcome back to Code in Motion. Today we're looking at LeetCode problem number 572, Subtree of Another Tree. Now before we get started with this example, I highly recommend you guys go through my blog where I talk about LeetCode patterns, specifically the patterns around binary tree traversal, since this is going to help you out a lot in this problem. It's good to know the pre-order, in-order, post-order traversals and the difference between the two for one of the solutions we're going to use later on. I also recommend you to solve and check out my video for LeetCode problem 100, same tree, because we're going to reuse the existing solution for this problem for the current problem as well, and it's really cool to see how they connect to each other. So let's actually start now with this problem. You'll notice that it's an easy, but I actually disagree. I think this is a medium level problem, but it's also a good problem to get really familiar with trees. We have two binary trees, root and subroot, and we need to return true if there is a subtree of root with the same structure and node values of subroot. Otherwise, return false. Basically, what they're asking us is that we have a main tree called root. We also have a different tree called subroot, and we want to know if there is some sort of subtree in the root that is identical and equal to subroot. And you'll notice in example 1, there is 142 is equal to 142, and so we return true. So let's actually take a look at these trees. And the algorithm we're going to use at first is actually a pretty straightforward one. It's like the brute force solution of this problem. For every single node inside of the root tree, we're going to compare it to the entire tree of subroot and see if they're equal or not. If we do find a match, we return true. If we find no matches, we return false. Now this reuses the solution and the algorithm for LeetCode problem number 100, which is why I recommend you do it first. Because in that LeetCode problem, you have to write an algorithm that can detect if two trees are equal. We're going to be invoking that algorithm for every node inside of root. So let's see how that looks. Let's scan the first element in the root, and that's a 4. In this case, 4 is the same exact root element of the subroot, right? So since the node values match, let's actually check if the subtrees are equal. So in this case, we're going to start a new recursive iteration, and we're going to recursively check, are these two trees equal, starting from the root node? So the nodes are equal in this case, 4 is equal to 4, but now we need to check the left and right subtrees to determine if they're equal as well. So we go to the left subtree. In this case, the left subtree is 4 and 1. Is 4 equal to 1? No, it's not. So the trees are different and we return back false. In this case, the trees at the root nodes are not the same. So we just end the recursive call, we go back to node 4, and now we're back at the main recursive call at node 4. Now, since we didn't find a match at the first node 4 at the root level, it doesn't mean that there isn't a match. It just means that there is no match at that node. We still have to check if there's a match in the left subtree or the right subtree. So now let's go to the left subtree. That's going to be the other 4, the second 4. So let's highlight that in green. And now we notice that this 4 is actually the same as the root node's value in subroot, right? They're both 4. So let's actually check if they're equal or not. Let's check if these two subtrees are equal. So we're going to start a new recursive call, and we're going to recursively check if these two trees are equal. So 4 is equal to 4. We're good for the root node. Now let's recursively check the left and right subchildren. So we go to 1. 1 is equal to 1, so we're good. And on top of that, these are both leaf nodes. So this is kind of like a base case, right? If the leaf nodes are equal, then there's nothing else to explore since the children are just null. So we go back up to 4, and now we need to check the right subtrees. In this case, it's just a leaf node of 2, so they're equal. Now we go back up to 4, and the nodes at 4 were equal. They had the same value. The left and right subtrees were equal as well. And so we found a match at 4, right? These two subtrees are identical. They have the same shape and the same values. So we found a match over here, and we're done the algorithm. We actually found a subtree in root that's identical and equal to subroot. Now, what's the time and space complexity of this? This doesn't seem that optimal, right? For every node in root, we need to scan the entire subroot in the worst case. And this is actually going to be an O of n times m time complexity algorithm, where O of n is the size of root and O of m is the size of subroot, because for each node, we need to scan the entire subroot. In this case, the space is just O of n, because in the worst case, we have O of n recursive calls on the stack when scanning the root nodes. So let's take a look at how we could be more optimal. The problem with the previous solution is that for every node in root, we need to scan the entire subroot, which is a lot of repetitive work and redundant calculations. Wouldn't it be better if we could just scan each tree only once and then compare them at the end? So we could actually do that. We could actually traverse through each of the trees and create a string that represents that tree and then just compare the strings at the end. And so we're actually going to be using a serialization technique. Now I want to talk about the format of the serialization that we're going to be using. So I'm going to represent a node as the string, parentheses, the node's value, comma, the left subtree, comma, the right subtree, and then close parentheses. In this case, a base case, for example, a leaf, would be represented as the node's value, comma, n, representing null and null, right? So that's how we're going to take care of the null values to encapsulate the shape of the node and the shape of the tree inside of a string representation. So let's actually calculate the serialized string for the root first and then the subroot after. So let's start with the node 4. In this case, all we have is the open parentheses and then the number 4 because we need to recursively calculate now the left and right subtrees. Now you'll notice that we're taking the node's value first. So this is actually a pre-order traversal. If you reference back my guide on all the LeetCode patterns, this is actually a pre-order traversal, which is super useful for serialization techniques with binary trees. So we take 4 and now we need to recursively calculate the left and right subtrees. So let's go left first. We have another 4. So let's add that to the string. Now we go left again. In this case, this is a base case. 1 is a leaf node. So the serialization string is 1NN. Let's add that to our serialized string. And now we go to node 2, right? So from node 4's perspective, we calculated the left serialization string. Now we need to calculate the right one. In this case, 2 once again is a base case. It's a leaf node. So we add 2NN. Now we finished at 4. So we go to 5. At 5, this is a base case. 5 is a leaf node. So we just add it, 5NN. And then we go back up to 4. And in this case, we calculated the serialized string. Now we need to do the same exact thing for the subroot tree. So in this case, we have 4. We go left. This is the base case. We have 1NN. So let's add that to the string. Now we go to the right child, which is 2. We add 2NN. And then finally, we go back up to 4 and we close out the parentheses. All right, now we represented both trees as strings. We only iterated through each tree once. And so the final check is to detect if the serialized string for the subroot exists in the serialized string for the root. And in this case, it does. We see a match, right? And I highlighted that in purple over there. And so that actually implies that we found a solution. And the time complexity of this is O of n plus m instead of O of n times m, because we only scan through each of the trees only once. And the space is O of n plus m as well, because we need to keep track of each serialized string. So let's code out the brute force solution for this problem. And notice that I actually copy pasted the result from LeetCode question number 100 is same tree over here. We're going to be reusing this solution. But for the sake of this problem, just assume that you have a function over here is same tree that will tell you if two trees are identical in shape and node values. We're going to be reusing this helper method in the current algorithm. Now I'm going to define a helper method for this current problem. It's going to take in the root and the subroot. I'll just call these P and Q. Now the first base case that I need to check for is if the current node doesn't exist or if the root node is null, right? So if not P, I'm just going to return back false, because Q is always guaranteed to be at least one node. So if there is no P, then we know that there's no way these could be equal. Then I'm going to check if these are the same tree. So if is same tree, P and Q, then I'm done. I just found my result, right? Return true. We found a match over here. But if they're not, then I need to check if the left subtrees are equal to Q or the right subtree is equal to Q. So left subtree is equal to helper P.left Q. And likewise, I'm going to return left subtree equal, or I need to check if the right subtree is equal to Q. So I'm going to say P.right Q. And we're actually done the algorithm. Now we just return helper of root and subroot. Let's run this and verify it succeeds. And there we have it. So now let's code out the optimal solution. For the optimal solution, the first thing I want to define is the helper method serialize, which serializes a tree and converts it into a string. So the first thing is the base case. So if the node is null, we just return back capital N. Else, we're going to return back a formatted string. Now this is going to look a little funky at first, but bear with me. We know that we need an open parentheses and then a close parentheses, right? And inside of this, what do we want to include? We said we're going to take the pre-order traversal, which means we scan the current node first. So I'm going to take over here node.val, and in Python, the formatted string allows you to insert a variable if you include it inside of brackets. So that's what I'm doing over here. This string is basically saying insert the current node's value inside of this parenthesis. Then we're going to split it out by a comma. And then this is how we're going to actually do the pre-order traversal here. We're going to say serialize node.left, comma, serialize node.right. And what this is actually going to do is basically invoke the function again recursively for the left and right subchildren. And this is going to return back the finalized string that we need for serialization. Now what we need to do is basically get the serialized string for the root and the subroot. So root serialized is equal to serialize root, and then subroot serialized is equal to serialize the subroot. Now all we need to check is that the subroot serialized string is contained in the root serialized string. And we're done. Let's run this and verify that it succeeds. And there we have it. Thank you so much for watching. If you're interested in more content like this and seeing the Blind 75 in animated format, be sure to subscribe, and I'll see you in the next one.